It is 1922 when Charles Proteus Steinmetz, co-pioneer of electricity with Thomas Edison, goes on the WGY radio station to talk about how energy, technology, and automation will elevate humans out of hard physical labor and exploitation in the future.
Is civilization not for a minority depending on the labor of masses of slaves or serfs, but a real civilization of benefit to all the members of the human race.
Across town, 5-year-old Harold Chestnut plays in his parents' yard. No one knew then that through engineering, he would carry out Steinmetz's dreams to reality during the most momentous times in the 20th century. Robotics, computers, and servo mechanisms are the basis of today's wonder technologies. All of these technologies use a common concept called automatic control and feedback systems. Harold Chestnut helped build a foundation for all modern control systems in the 1940s and 50s. Later in life, his focus shifted to using technology for peace and cooperation between nations.
Chestnut was a very great promoter. He was a very good promoter, good speaker, and very well respected among all engineering societies.
This is that generation that matured through World War II, so I think they considered that organizing IFAC was part of the task of rebuilding the world.
The world peace aspect was something that my father in particular spent a lot of time thinking about and a lot of time working with people on an international scale.
And a privilege to be with Mr. and Mrs. Soichiro Honda.
The story of Harold Chestnut begins with his father's life on the other side of the world. I recall with horror the time when the general store operated by my parents was looted and destroyed. We were obligated to flee from our homes in the village in the middle of the night. Harry Chazanov. Harold Chestnut's father lives in Poltava, Ukraine during the pogroms. He and his parents escaped the persecution in 1905 to come to the United States. Eventually, the family settles in Raymond Hill, Connecticut with their own farm. Once settled in America, they changed their name to the more easily pronounceable name Chestnut. Harry gets a job as a draftsman for General Electric in the booming city of Schenectady. While there, he gets married and has a son, Harold, who was born in maternity home in Albany in 1917. The boy discovers a talent for swimming. Harold, also known as Hal, was tall and lanky, and despite his size, his long, steady swim strokes could beat anyone in a long-distance freestyle swimming competition.
We swam competitively in high school because then Schenectady had 3 pools.
Hal also tends the YMCA Camp Ginger Cook at Pilot's Knob on Lake George in the 30s. He loves the outdoors and becomes a swimming instructor. He works alongside John Mahoney, who would later become a legendary local swim instructor in Schenectady.
He was a partner in crime of John Mahoney, who was taught, I guess, everybody in Schenectady, all the men in Schenectady, to learn to swim for about 30 years.
Lake George in the Adirondacks is known as the Queen of Lakes. At 32 miles long and flanked by mountains, it's a natural wonder. One day, while peering across the waves, John and Hal decide to challenge themselves. So they swim 2 miles across turbulent water from Pilot's Knob to Bolton Landing. In addition to an interest in nature, Hal develops a love of science and shows a natural talent in his teen years. He becomes the valedictorian at Knott Terrace High School in 1935. He's offered a scholarship at MIT, and soon he's on his way to Cambridge. He works diligently for 5 years, completing his BS and MS degrees in electrical engineering 1 year early. Harold was done with college, but he felt his education was not quite complete just yet.
My father got out of college. He and a college friend took a trip around the United States, which was probably in 1940.
With a used Plymouth and a bundle of traveler's checks, Harold and his friend from MIT, George Sr., leave Schenectady, driving south along the Hudson. Perhaps they were aware that the diverse America they were about to see would soon disappear once the interstate highway systems were completed in the near future. Hal takes detailed notes on everything from geology to the local people. In Tennessee, he writes,
"The kids down here all seem to go barefooted. Also, the traffic lights in some places go green, yellow, red, from top to bottom, instead of the reverse order." Outside Pasadena, we drove through orange groves. A number of "all the orange juice you can drink for 10 cents" signs brought us to a stop.
In San Francisco, they run into some car problems.
We then went over to get the car. As we feared, the cost was plenty, amounting to over $30. That was bad, but when the fellow showed us a crack in the manifold that he hadn't touched, but would cost another $10 to do, we were nonplussed. With little time available and negligible spare cash, we elected to let the thing ride and hope for the best.
The two camped, visited national parks, and mingled with the locals.
The tall redwoods are fine to sleep in because they prevent the morning sun from waking you at the crack of dawn.
Hal and George hiked the canyons of the Tetons with Evelyn Langmuir, niece of Schenectady scientist Irving Langmuir. Harold takes notes on the Indians of the Southwest, who still live a nomadic, wild lifestyle at the time. But as this trip through the peaceful countryside rolls on, something ominous is growing far away.
Picked up some gas in Savannah, Tennessee, where we found France had capitulated to Germany's terms. The fellows spoke as though they were pro-ally. Also, talk indicated that the fishing in the TVA lakes was good. Leaving Oklahoma City, one comes out into real farm country. Late in the afternoon, we spoke to a big, blonde, fair-haired gas station owner about things in general. It seems that some of the Germans out here think Hitler is okay. Most of them, however, are anti-Nazi.
Hal returns home from his trip and continues with a co-op program between MIT and General Electric. World War II begins, and Hal is among 25 engineers sent by GE to the MIT Radiation Laboratory to work on the Mk-56 Navy guns, as well as some other top-secret projects. Bob Mayer, Hubert Schlafly, and Bill Chapin lead the radar team.
For that, he and Bobby went over to Boston. We never knew what they did at the radiation lab because that was strictly secret. They were not allowed to say anything about it. We knew that they were going over there and they were working on war work, but what they did, they couldn't tell even their own wives. He got pretty knowledgeable in servo mechanisms and regulating systems.
Harold moves into the Aeronautics and Ordnance Division at GE. His responsibilities included solving problems in automated control.
If you think of the contribution that was needed in order to win the war, it just boggles the mind. As a matter of fact, the amount of goods and services that had to be moved around. And we here in Schenectady were responsible for a considerable portion of that effort.
In 1943, Harold Chestnut is assigned to work on a new gun turret. So far, gun turrets like those on the B-17 have a number of problems. Gun operators had to sit or stand in freezing temperatures for long periods of time. In these conditions, gunners quickly became cold, fatigued, and made errors. Each of the B-17Gs had 13 guns and required a large crew. Turret operators were in a direct line of danger.
We had a total crew of 10. I heard a kind of a loud bang, and I looked over my head, and there was a small walk-around oxygen bottle. And of course, they had some glass window up there, and this piece of flak had gone right through both sides of the window, and probably about an inch or two from hitting that oxygen bottle.
New automatically controlled turrets could allow more accuracy and safety for the crew. Perhaps the largest advantage is that the cabin could now be heated and pressurized, allowing the bomber to go to much higher altitudes. The new turrets are fitted on the Boeing B-29, a new high-tech long-range bomber.
His job involved, as far as I know, mostly the gun control on the B-29.
The turrets were controlled by a fire control computer designed by Hal and his team. This computer was really an electromechanical device that calculated distances and angles. Mathematic equations such as this parabola were manifested into actual mechanical parts within the computer.
The problem with doing fire control is to predict where the target will be.
The radar and conical scan tracking antenna targeted incoming fighters. Now, one gunner could sit in the fuselage of the airplane and operate multiple turrets at the same time. One challenge was that as an airplane approached, the radar signal gave back reflections of varying amplitude. He used control theories to run averages of the signals so the turret could smoothly follow the target. The fact that this could be done before modern transistors or semiconductors was quite an achievement.
The problem was to make the mechanism in the box perform. In those days it was in synchros. This whole thing must stand the vibration of being in an airplane.
The plane is introduced in May of 1944. The results of Chestnut and his team's work is effective, to say the least. It took an average of 500 fighter attacks to take down a B-29. General Electric then starts to produce up to 2,400 turrets each month. Harold Chestnut was breaking new ground in automatic control design, but this field had ancient beginnings. The first known example of a control system was in 1400 BC. The ancient Egyptians used a bucket-shaped vessel to make a water clock. The size of the hole in the bottom and the shape of the container controlled and steadied the flow of water to make an accurate time indicator. Another major step forward was in the 1850s. Until then, ships' rudders had been controlled by a series of mechanical connections from the helm. As ships got bigger, the hydrodynamic forces on the rudder and the gear ratios became so great that it was slow and difficult to steer a large vessel. French design engineer Jean-Joseph Farquhar coined the term servo-moteur when he invented a system which controlled the rudder using a specialized engine. The need for control systems increased greatly with the advent of electrical power. The electric arc lamp provided urban lighting on State Street in Schenectady, New York, from the 1880s until the early 20th century. It depended on a constant, regulated flow of electricity. In the power station in Building 31 on Erie Boulevard, feedback circuits fed signal back into the amplifier circuit, which helped produce more uniform power transmission, even with extreme outside temperature variations. Schenectady became a testing ground for new control technologies, as Thomas Edison and Charles Steinmetz conducted their work here. Control engineers solved problems on everything from steam generators to the vacuum tube.
In science, we learn how to analyze and explain the behavior of something which usually is physical, and we stop there. The control engineer then says, now that I understand how that physical system works, how can I add to that, this is the man-made part, so that it will perform better, or it will produce a future that I like better. So that's the engineering approach, but it is also the heart of control engineering, which Hal was a pioneer in.
You know, virtually all the electronic devices we use, the cars, are filled with different ways of using a term that my dad used a lot, feedback, to make sure that things were going the way you wanted them to go.
But feedback, properly analyzed and controlled, becomes a powerful tool in the hands of the modern engineer. Feedback can accurately, efficiently, and reliably govern guidance systems, servo systems, power supplies. The list of applications is limitless.
The simplest example of a control system is the thermostat in a house. We input the data. The device tells the heater to activate. That is simple, but the important part is the feedback system, which is the thermometer in this case. The feedback information, or current temperature, is analyzed and tells the heater to shut off at a desired point. While the Second World War rages on, Harold Chestnut works on aviation technologies. He works on gyro instrumentation. He creates a new gyro system for General Electric, which will remain in use for decades to come. The gyro becomes an important part of the feedback system for autopilot systems and navigation of planes and rockets. He also works on power systems for aircraft, inventing a better dynamotor. A dynamotor converts DC battery power to different voltages for other uses around the aircraft.
I worked for the Aeronautics and Ordnance Systems Division, and we did a lot of work for the military on control systems for airplanes, like for damping systems, to correct for the fact that some airplanes, when it got up to Mach 1, in other words, over the speed of sound, the things would develop bad, say, pitch oscillations. And his particular specialty was making an electronics model of a big airplane which had this problem.
At this time, Hal belongs to one of the many YMCA clubs in Schenectady. The YMCA is an important part of the community during and after the war.
He was an OIC, Haute Yokor Club member. There were a lot of young people in Schenectady at that time, you know, people just out of college. We would go on hiking trips, camping trips, canoeing trips, skiing, all sorts of outdoor things, plus square dancing and so on.
When Hal attends a dance at the Van Curler Hotel, sponsored by the YMCA and the YWCA, that night would change his life forever. As president of the Odeokla Club, Hal greets the visitors at the door. And this is how he meets Irma Ruth. It wasn't long after that they'd spend all their extra time together.
She came from Colorado, and right out of college, like I did, only I was 2 years ahead of her. And she came on GE test, worked out at the Campbell Avenue plant. Not many women went into engineering. She was really a pioneer to come to get a job as a GE test man.
I was charmed by her, just even seeing her across the room. I would say the choice that we had to get together and be married was, as far as I'm concerned, the best decision I could possibly have made.
The couple marry in Colorado Springs in 1944. Hal continues to work on advanced systems at General Electric. The Korean War will continue to drive up production and employment at GE in the 1950s. Hal trains young engineers in the GE test program. Eventually, Hal is urged to publish a book on his newly discovered field of work. He teams up with Robert W. Mayer to write Servo Mechanisms and Regulating System Design, which is published in 1952. Hal's book on this new subject was a hit all around the world.
Well, he wrote one of the most famous early books on control in the 1950s. And so that had quite an impact on young people in the field.
If you're in the control field, you have to know Hal Chestnut in those days.
Worked by his book, Chestnut Meyer, which was at that time the most important and best standard handbook for automatic control.
You see, the books that I wrote were published in many languages.
Because at that time there was not a lot of communication across international borders, and books did flow across international borders.
In the next few years, Harold writes and edits several more books for the John Wiley book series. The book Systems Engineering Tools and Systems Engineering Methods fast becomes a staple of aspiring engineers. One reason for the success of the book was the author's style.
It was an engineer, not a theoretician, writing about a theoretical topic. And so it had a practical flavor to it that was important.
Back at work, Hal gradually shifts his focus from automatic control to the new field of systems engineering. Right at the start, Hal encounters resistance to his ideas.
He was appreciated for being a good engineer, G and design and a lot of things. But all this over system engineering and so on, most people thought it was a waste of time or couldn't realize it. And then he was very appreciated in Japan because the Japanese worshipped him. Just like they on quality control, they figured out that was the thing of the future. We need to learn from Chestnut, you know.
Hal was a development engineer in General Engineering Lab and Corporate R&D. He was one of the early men who recognized the needs for system engineering in building electrical systems of all kinds, that they were more than just a simple problem, it was a big problem.
Systems engineering is the management of complexity. When you need to develop a difficult and complex technology product, like a NASA satellite or even a laptop computer, you need to make an order and feedback process that manages the very way a company creates that product. This organized system is very important for saving money and avoiding a faulty end product. Bell Labs started the systems approach in the 1940s, but Hal brought it to international attention.
That systems approach was always the big picture, and so this notion of how to look at big problems.
Systems engineering is important in the world because so much of the world consists of systems. There are economic systems, there are technical systems, all airplanes are technical systems, all technology devices are technical systems. So it is fundamental to everything that makes the world go around. Maybe not in art so much, but in many other fields.
In 1955, the Aeronautic and Marine Division is discontinued. The same teams that had worked during the war on radar guidance and control are put into a variety of new technologies. Hal makes notable contributions in jet engine control, steel mill control, nuclear power plant controls, rocket guidance, and high-power transmission.
Well, when I joined, there were two groups in controls, one at the research lab, which was a theoretical group, and one at downtown, which was the general engineering lab, and Hal ran that.
We were the key control group at General Electric Research and Development Center. I was working on jet engine controls. Even though the jet engine looks so difficult, but looking from the control point of view and systems point of view, you can control this in a very mathematically based, model-based techniques. And because of his effort and his foresight, many of his work already has been implemented in jet engine control as we know today.
Many developments in control technology continued after the war. However, 5,000 miles away, a new leader in control technology was emerging. The advancements there would soon demand international attention through an incredible set of firsts.
The end of 50s and the beginning of 60s was a golden era for Russian math. It was a period when people believed in research. They believed that science will help them to live a better life.
Harold will soon find himself in the middle of international science and engineering amid difficult political times.
To set up an organization across the Iron Curtain was very unusual.
One of the things it stood for then was bringing some measure of bridging between the Soviet Union and the West.
In the next episode of Wizards of Schenectady, you will see how Harold transitions into a leader of the engineering world and will bridge the gap between engineering, social, and environmental issues. That's all on the next Wizards of Schenectady.